Very good afternoon, dear faculty members. I request please inform your colleagues or friends to join the session as soon as possible. We have very less participate today. So I kindly request inform the participants to join.
Shweta ma'am, can you confirm? Am I audible? Or am I screen visible?
Yeah, good afternoon, sir. You're audible.
Good afternoon. Can you please confirm? Is my presentation visible to everyone?
Yeah, yes, sir. It is visible.
Okay. Just a second. Yeah, okay. So, welcome back, everyone. Yesterday was about understanding quantum information, and today we formally start building it with it. And by the end of this session, you will have written real circuits. You will be creating entanglement uh, with your own hands, and you would have seen a bell state appear on your screen. That is where the entanglement, you can say, we see the magic of entanglement. So a quick warm up before we formally start the session. I hope everyone has gone through the diskette installation video, and they have run the Hadamard gate to check the superposition and all, that how superposition actually works. And you must have got this expected result, that is 50% times 0 and 50% times 1, that is an equal superposition. So please uh, confirm this from your end that this has been done, because whatever we will be doing today, it is building on the previous ideas that we have discussed yesterday. And today will be, you can say, more hands-on than just you can say theoretical foundations. So even if someone is not like hasn't like installed Qiskit, they can do so in the background. They can go through the lecture also, and maybe uh, do this activity in the background. It's just you have to have Anaconda or Miniconda, whatever is okay with your system, Visual Studio Code, and you will have to create a virtual environment in this virtual environment, so as to do everything in that particular virtual environment inside VS Code, and through that you can do this script coding. Now, where we started with. So yesterday we discussed 5 core ideas, namely qubit, superposition, measurement, interference, and entanglement. And now we are moving towards that, how this can be written precisely in the terms of states. These states, how we can represent them. Then the idea of gates, which is very, very pivotal to the idea of unitary transformation or the unitary evolution that we were discussing, that how we transform from one state to the another state. That is done using the single qubit and multiple qubit gates. One of them we had, actually two of them we had discussed yesterday. That is the X gate and the Hadamard gate, but we were not aware about what exactly is going on inside, what is the mathematical detail. So we will cover that a little bit. Then we will be building up the circuits that actually do something, not just toy sets. So we will alternate between some concept bursts, and will move on to hands-on practice also. So it will be a kind of a alternation between that. So please keep your notebooks open. That is the VS Code notebook open. Take open Jupyter notebook in VS Code itself, so that we can do this step by step. So this is the agenda for today's session. We start with the quantum states, where we describe that how a quantum state is seen, and the part B is all about the gates, the gate toolkit, the verbs of quantum computing. These XYZ, Hadamard gates, phase gates, these are single qubit gates. And then we move on to the third part, that is the multi-qubit gates and the entanglement, because entanglement can be achieved only using from two or more qubits itself. And for that, we will need one specific mathematical idea, that is the tensor product. Very basic idea, not a problem. It's just tensor product. Everyone is also aware about this. Is like array of matrices. It is like that, or you can say matrix about matrix. In any way we can say that. So this is the idea around entanglement, and we'll specifically see four different types of Bell states, how we can prepare these Bell states, and the no cloning theorem. As we were discussing very briefly, we just had gone through a single you can say idea that what exactly is happening in no cloning theorem, and how this algorithm, this theorem, is the basis of post-quantum cryptography. So when we say that how the cryptography will evolve, how the communication will evolve, this theorem comes in quite handy. And specifically, the circuit model and the workflow that we will be focusing on, that what exactly is the general workflow of quantum computing you can say paradigm. And we will be specifically seeing some labs, explicit labs, quantum coin toss, and how is it different from a classical coin toss. uh, then the quantum random number generation, that is an uh, you can say abstraction of generalization of this quantum coin toss only, and the Bell state generator, that is specifically coming from this Bell states. So this is the agenda for today, and we will be specifically discussing everything in detail. Now, a quick recap of what was discussed. So let us tighten up yesterday's picture. Single qubit is just a little vector of two numbers, as we were discussed, and the amount of zero and amount of one depends, it varies, that how the values will come up. And those numbers, that is alpha and beta, are what the amplitudes, and squaring them is the squares will give us the measurement odds. So this is the foundation that we will build with every gate and circuit. So it's worth saying once again. And the computational basis, there was one simple, I think, kind of a typo, or you can say it was also correct, it is not a problem, that this zero state, as we see it in terms of column vector only. So yesterday I had not written this uh, transpose, so that's also okay. But yeah, formally it should be written like this, because this zero is a column vector. We write in the terms of a column vector. One is also a kind of a column vector. So how we see this, it is like alpha zero So in this particular sense, that alpha is giving us this and beta is connected with this. So here we will be getting alpha, that is this amplitude, and in here alpha into 0 plus beta into 1, we will be getting actually beta. So that is how you understand the idea of these computational bases. So this is the correct way to write it. If there was any confusion, please see to it. So this is with this idea, we are now moving towards the basis states, and these are very important basis states, and how we are coming to the understanding of these plus and minus. We had discussed this briefly. We just uh, we had just seen it from a surface level point of view. Now we will be deep diving into it, because without these states, there is no point of discussing interference, phase, anything like that, because these we can say states are very important. So the plus and minus, as you can see, everything is same, nothing is changing. The only change is there, that is this sign, plus and minus, that is they are differing only in phase, magnitude remains the same. And actually, if we say that are they same state, they are not. They both are 50-50. That is, until unless we are measuring it, it is a 50-50 superposition. Just like we saw yesterday, that probabilities were 50-50 exact when we just put up a Hadamard onto a qubit. So this is what we get in a particular state. Now, let me show you quickly. That think I will have to show the screen. Yes, yeah. So in Composer, what I'm trying to show you is, if I put this Hadamard onto this qubit, what exactly are we getting is this state, that is the plus state. Okay. Now this plus state is what we were seeing, that is 0 plus 1, that is 0 state, 0 qubit plus 1 qubit divided by root 2. But how do we get the minus state? For that, we need to first change this qubit, that is the initialization of this qubit, to 1. Right now it was 0, now it is 1. If you see this is the first state. If you see probability, the state vector also, and the amplitude. So now we are at you can say qubit state 1. As soon as we apply Hadamard to it, we will be getting the minus state. Now I hope everyone is understanding this. That is 0.707 and minus 0.707. So we'll do this back and forth, that we will be coming towards this uh, idea of how actually states are built up. So I am hoping this is clear to everyone, that how plus and minus states, minus state are like built. Okay. Let's come back in here. Yeah. So with this, we move on to the idea of the amplitudes, the global phase and the relative phase, as we were discussing. So if plus and minus differ only by a sign, which signs actually matter? That is our say a specific question. So here's the particular rule. What's that? A phase between 0 and 1, that is relative phase, is real and physical. That is what we discuss in respect to relative phase. That you can say phase between this 0 and 1, the sign just we saw. This is the example. This is the plus state, that is Hadamard applied onto 0 state, Hadamard applied onto 1 state. This is how we get both of these states. And a phase between but we have covered the idea of relative. Now, an overall, you can say, phase on the whole state, that is what we call as global phase, and this is why it is invisible, because it is not done on a specific part, you can say states specific, you can say concretely. It is an abstract way of saying that we are applying the phase on the whole state. So the overall change is not seen, not visible, it is unobservable. So that's why this psi and e raised to power I theta psi, that is the complex, you can say amplitude, we both of these values are coming as same physical state, nothing is changing, so no one can detect it. That is why it is unobservable. And that's not exactly a technicality, it is not a kind of a technicality, it is exactly why we can draw uh, any single qubit as one clean point to a sphere. So on a sphere. So when we say that, okay, how a particular qubit can be drawn on a Bloch sphere, just as we saw yesterday, that if a qubit is drawn nearer to the south and to the north pole, then it will be giving us the zero state. If it is drawn near to the south pole, it will be giving the one state. But besides that, if the qubit is in any other position besides north pole and south pole, it will be in a kind of a superposition or any other state. So the idea of relative and global phase is governing the understanding of how local effect and a global effect comes into play. Now, moving towards the Bloch sphere, that it is a kind of a working tool where every single qubit state is a kind of a one point on it. That is, north and south pole are 0 and 1. Besides that, the equator, as we see, that is the part that at the center is superposition, and going around the equator, when we move around the equator using different gates, is what known as changing the phase. And this is what we will specifically see with respect to three different phase gates, that is the Z gate, the poly Z gate, the S gate, and the T gate, that is coming up next. So the idea of a X gate, or you can say a poly X gate, is just to flip the qubits. That is, if we have plus, just if we have 0, just flip it to 1, and if we have 1, then flip it to 0. That's the basic idea. So every single qubit gate that we are single qubit state we are seeing is like one point on that particular sphere. Also, because every gate, why do we care in with the idea of Bloch sphere? Because every gate we are about to learn is simply a rotation of the sphere. It's nothing else. Whether it is a poly X gate, poly Y gate, poly Z gate, Hadamard gate, S gate, that is a phase gate, T gate, that is another phase gate, or any we can say single qubit gate. Now we are specifically discussing about single qubit state. That's why we are not moving towards the entanglement gates, that is the C naught gate, or anything like that. So all of these gates are what? A rotation of this sphere, that is the Bloch sphere. And hold on to this thought, it will make the whole, you can say, visualization, you can say, very clear, instead of just algebraic operations. Right now we might understand, okay, this is some algebraic operation being done, but actually we will see this step by step in Bloch sphere in few moments. So the quantum gates. Now, what exactly these gates are, what are the operations, and how we actually, we can say, apply these operations to the particular qubits. So a gate is an operation on a state, and mathematically, it's just a matrix, nothing else. That is why linear algebra is the most important backbone of quantum computing. Uh, the best source of linear algebra is to go through the course by Gilbert Sprang. He's the one of the most can say famous the pioneer in linear algebra. The basic understanding of how actually the vectors, what exactly is a vector space, how we see the linear combination of basis states, what happens when we see the basis and dimensions in a new way, and the idea of linear transformations, where the idea that we are just using, that we have one linear operator. Suppose we have one linear operator, how we transform one from one state to the another state, that depends on this linear operator. And this is what the quantum gates are. They are the operations that we are performing, and these operations are in the form of what? A matrix only. So whether we go through any of the you can say gate XYZ, Hadamard, or any gate, even the 2-qubit gates also, C naught gate or Toffoli gate, Fredkin gate, many gates are there. Every gate has some specific matrix, and we apply the operations through those matrix only. So the word that matters here is exactly this word. That is the unitary, you can say, idea. And what this unitary means, that our operations are reversible, as we were discussing yesterday. That every operation that we perform in quantum computing is reversible. Only one exception is there, that is the measurement. Every time we discuss about measurement, because measurement is not a gate, so we have to picture it like this only. So picture this gate as a rotation that never loses anything. And the idea of a single qubit gate is seen in the terms of this 2 by 2 unitary only. That is the matrix that we will be building up. It will be a kind of a 2 cross 2 matrix only. So this understanding of measurement is why important, why we are discussing measurement. That is a kind of a different operation. It is nowhere close to being a gate, because we have to come back to one specific operation, that is no cloning and no cloning theorem. So we need to understand that this measurement, why it is pivotal when discussing the reversibility, because this no cloning idea will be harnessing this idea of measurement, where we will see that how measurement not being reversible is actually giving us the intended quantum advantage, or you can say the kind of quantum communication and teleportation and many things that we rest upon. So this is the keep this idea closer to your heart, that what exactly is happening with respect to measurement. So it is a kind of a contrast. Now, with respect to the reversibility, everything that we are doing is reversible, and this single principle is explaining the three different principles that we are seeing today. First of all, why gates must be unitary. That's very important idea. Why you can't copy a qubit, that's another understanding, and why measurement is special. So when we say that gates are unitary, the goal is to focus on that there is no information loss. Because if the information is lost, as we see generally in when we discuss computer networks in computer science, we go through different protocols, many protocols, that how the communication is actually done, and OSI model and many things are discussed. And in that particular understanding, we see that when there is a gargle data, and then how the communication can be done, and if there is some intruder, in the communication channel only, then how we can keep say keep, we can say safely keep our data. That's very very important aspect that is discussed in computer networks field. So the goal of preserving the information, this is where the idea of reversibility comes in. It kicks in. The first benefit, that is, we are not losing any information. Then contrasting with the classical logic, everyone understands the how AND gate works. So when we say that A is 0 and B is 0, and we get the result as 0 only. And again, if we say that A is 0 and B is 1, and we again get 0, how are we going to come back to the conclusion that whether this 0 0 input gave us 0, or the 0 as output, or 0 1 inputs gave us 0 output? So this is where the idea of this AND or the classical gates, they erase the information when we have two inputs and one output, and they cannot be undone. Whereas quantum gates never erase that. So this is the practical idea that is coming up in the contrast with the classical logic. And the idea of measurement, as we have been reiterating again and again, as it is reversible, it actually destroys superposition. So we can't go back to the we can say the condition that we started with. That same experiment we were discussing, the Schrodinger's cat experiment, that whenever after we have observed that the cat is dead or alive, whatever it is, we can't go back to the same condition that we started with. So this is very very important. So the idea that when we tied them together, this actually is giving us the understanding of how every point, every you can say all these three ideas are quite special, and they actually lead us to very profound ideas, including no cloning and the you can say quantum communication and many more things like that. So this is the basic understanding of, or you can say this basic premise of why we need to understand the unitary idea, that is reversible, why these operations are reversible. Okay, let us now move on to the first gate, that is the poly X gate. This is simply the bit flip, and it is the friendliest gate, but the simplest gate you can see, and it's the quantum knot. It's like the quantum knot. So it swaps 0 and 1. And on Bloch sphere, when we see it, it is like a turn or a half a turn around the x-axis. Let us first see the all the three gates, or all the four gates, x, y, z, and h, and then we'll move on to the visualization of the Bloch sphere, and then the hands-on part, that how these gates can be implemented. So the idea is that when we apply X gate onto superposition, in you can say uh, the change is the will be there. And what's the change? It will be swapping the two amplitudes, uh, and just the change will be in this particular amplitudes only, which is like always which isn't always like do nothing. It is doing nothing. We apply X to the plus state and nothing changes, but we apply plus to sorry X to other states and it changes something. If we apply X to the minus state, there will be some change, but uh, that's not the case when we apply X to a plus state, that is in a superposed state. So the idea that we understand from this is, it's just a bit flip. There is no phase flip that is going on. For phase flip, we have the other gate, that is this poly Z gate. It is quite but important one, and it actually changes it leaves the 0 as it is. That is, there is no change done in the this 0 qubit on the state, but it flips the sign of 1. and we'll see that why it flips the sign, what's the matrix around it. Quick recap that this the matrix around it is what it will be 0 1 1 0. That's the matrix. It is simply the basic idea of the X gate. Whereas for the poly gate, what poly Z gate, what we say that it will be just changing the phase and not the probability. No probability change will be there. So when we measure in the usual basis, that when we do the measurement, Z seems to do nothing, and we will be getting the same 50-50 idea. But as we are understanding the change, that is Z is changing 1 to -1, we also see the same understanding, but that it turns plus into minus. When we have a plus, that is a superposed state, when we apply Z to it, it will be changing it to minus. And that hidden change is exactly what interference will later exploit. This is the important step. That is why these simple looking gates, whether it is X gate or Z gate or Y gate, they are important, because this particular gate will be actually exploiting the idea of interference just from a single phase flip or the bit flip. So Z is our first phase tool. So that's another idea. And lastly, very important gate, poly Y gate, and it is a combination of a bit flip and the phase flip. So what exactly is this doing? It is just X and Z are happening together, and which is why there is an I, there is iota in its matrix, that is it is imparting some complex amplitude. And on the sphere, when we do a half turn about the y-axis, we will see that how this actually works. The takeaway is there, is that X, Y, and Z are a natural trio, and these are like the three half turns about the three axes, different axes. So X turns around 180 degree about in the Bloch sphere. It is the X gate is a 180-degree rotation about the x-axis. Then Z is a 180-degree rotation about the z-axis, and Y is about y-axis, and together they are the building blocks for describing any single qubit operations. And lastly, the Hadamard gate. Before going onto the phase gate, other phase gates, we'll first visualize these, and then we'll come back to the SNT gates. So this is the last gate, that is the Hadamard gate, the superposition gate. This is the like the star of the show, and we will be using this more than any other gate, and it turns into an even superposition, that is the plus state, and it's the bridge between the certain world and the quantum world. That's the basic idea, and it is its own inverse. That is, when we apply Hadamard to a qubit, and again apply Hadamard to a qubit, we will be getting back to the same state, that is the zero state. And uh, we'll verify this just in a moment. And every interesting circuit that we see, whether it is any algorithm that we will be seeing tomorrow, Deuce-Joss algorithm or Grover's algorithm or Bernstein-Wazirani algorithm or Shor's algorithm, they start with the idea of Hadamard only. No algorithm can like start without Hadamard, because without superposition, you can't even take a single step forward. Okay, so now let us do one thing. Here it is. Okay. I'm sharing my screen fully so that you can see. Now, let's do one by one. First of all, in IBM Quantum Composer, when we will go towards our the VS Code setup, and we'll see that what exactly is happening one by one. So, starting with the idea, we have the X, that is the NOT gate. So NOT gate, when we apply, it's just simply giving us the, we can say, the swap. It is just swapping. Again, if we apply not, we will come back to the original position, that is its own inverse. That's the basic idea around the X gate. Now, this is the simplest idea, and I hope everyone understands that what exactly is happening with respect to X gate. Z gate is a little bit different. Now, right now we are going to see four different operations. Z gate onto 0 qubit state, Z onto one state, state 1, Z onto plus state, and Z onto minus state. And we'll see what exactly the change happens. So first of all, when we apply Z onto state 0, there is no change. If you see, that's what we discussed. Let me do it again, and so that you can see the state vector. No change. But if we apply it to the X gate, that is the one state, what we will be getting? We will be getting the, if you say, there is a phase change. And why is this phase change coming? Because of the matrix that we have with respect to the idea of Z gate. That is, we have one change in the terms of the matrix. Let us go back to the matrix. What's that? If you see this 1 0 0 minus 1, when we multiply this matrix, when we apply this matrix onto the state 1, we will be getting a change. One thing I can do quickly, maybe I can make you show it on the whiteboard so that everyone can understand quite quickly. I hope my screen is visible. That's why whiteboard is visible. So if you see that the state that we are just putting out, so this is Z 1 0 0 minus 1. So we are saying that when we apply this to state 1, that is, let us put our states. One is 0 1, then plus is 0 plus 1 divided by 2, and the minus 1 is 0 minus 1 by root. Okay, so we have this Z gate. Now, when we apply this Z gate to this state, so what will be there? 1 0 0 minus 1, simple matrix multiplication. 0 1, what we will be getting? 1 into 0 plus 0 into 1, 0, and 0 into 0 and minus 1. So this is what we get, and this is exactly what you can see in here. Simplest idea. Okay, like this, if we do the same with this plus state, that is the how this plus state is, you can say you get go back to the idea of Hadamard. Go back to the idea of Hadamard. You see this, how this Hadamard matrix is stacked up. So the idea of a Hadamard matrix is like this: 1 by root 2, 1 1 1 minus 1. This is how we see the Hadamard matrix. Now, how we get to this plus matrix? That is, when we apply Hadamard to 0, we get the plus. It's again simple matrix multiplication, nothing else. We keep this 1 by root 2 outside, and we just apply this matrix into this 1 0. And when we have this Hadamard onto 1, we get this minus state. That is, this is state. So this is the basic idea. Now, applying this Z, that is Z2 plus, what it will be giving us, and Z2 minus. So again, let us come back to this understanding. First of all, we'll do this. We'll keep put this into a superposition. Now this is in a superposition, that is we have now in a plus state. As soon as we apply z onto it, what we will be getting, it will be giving us a phase change. That is what the idea is all about, and this is what we were discussing in with respect to this z gate, that we will be getting a change in the terms of the uh, we can say plus state. So z onto plus, that is the superposition, will be getting the minus state. This is the minus state as you can get. What about if we have apply the z uh, onto uh, minus state? So for that, let me reiterate. First of all, we change the state to 1. Then we apply the header mark. See the change in the state vector. You see the header mark, we get a minus state, and then we apply the z. You'll see we will get a plus state. It means z is doing what? It is changing the phase. So when we apply z onto plus, we get minus state, and when we get apply z onto minus, we get a plus state. I hope this is clear to everyone what exactly is being done with respect to the z state. Now another you can say gate, that is the y gate. Now what's the y gate in this particular context? That is 0 minus I 0. And when we do this, 0 minus I 0, what happens when we apply y to 0, y to 1, y over plus, and y over minus? So let's try it first in here, and then see mathematically what exactly is happening. So when we apply y to the 0 state, what you see, you will see that 0 1 j, that is there is some complex part coming up. How we can understand that? Let us quickly see this. When we apply it to 1 0, why it is coming? So 0 into 1 minus I into 0, so it is 0. I into 1 and 0 into 0 is I. We can write this as I 0 1. This is how you can write it. Okay, so this is how we get this 0 comma 1 j. And mind you, Qiskit shows the complex numbers through j, although I had written like this I, that's okay because it's a habit of us to write the imaginary number with I, but Qiskit uses j to show the idea of a complex number. Now quickly we can see what happens when we change the qubit from state from 0 to 1. This is now one state 1. When we apply y to it, you'll see what happens. We'll get minus 1j comma 0, and this is the you can say the opposite of what we were getting in here. So it will be like this, minus 1 0. So this is what is actually written in here, minus 1j comma 0. I hope everyone is getting this. This is when we apply y onto 1. Okay, so this is what we get. And for the other two aspects, we will have to start with the header mod. First of all, we apply header mod, so it gets in a superposition, and then we apply the y, that is it. So if you see both of the parts, we are getting some you can say complex values, that is this will be uh, this minus 7.70 I or j, as you can see, and this is also j. And as we see the minus state, let us do it quickly in here. Now you get the state where both of them again they are imaginary or the complex. So this is the idea around this Y matrix. Now, why are we so focused on these particular ideas is because we need to understand that these specific gates are the source of what the advantage, the kind of advantage we are trying to see from different algorithms. After superposition, that is after applying this Hadamard, how different gates, how different uh, arrangements can be made so that we get to the intended result. This is why the idea of these gates are you can say pivotal for the understanding of these particular gates. uh, Next we move on to the idea of uh, SNT gates. So let me quickly. So we were discussing the Hadamard, and now the other two gates, that is the phase gates. So the idea behind this these gates is that sometimes we don't want to flip a qubit. We just want to nudge its phase a little bit, and that's what these gates, that is S and T, do. They are small. They do some small precise rotations of phase around the z-axis, and specifically the z-axis we are saying. So the 90-degree rotation and the 45-degree rotation, that's what is done in the respect with respect to these gates. So uh, two quick facts, that this is S gate is the square root of Z, as we can understand, and T is the square root of S. So they look like, okay, these are not that much important or minor kind of minor gates, but they are essential, because without fine phase control, that is that we are when we say that we are trying to nudge it a little bit depending on how the actually the phase is changing. Without these finer phase control, we can't build arbitrary quantum operations. You can we might build some generalized you can say operations, quantum operations, but many a times we need a deeper understanding of how a particular algorithm will work. Let us say, for example, we have a quantum machine learning algorithm that is built on the idea using we are using some quantum neural networks. In neural networks, the basic understanding is what, when we do the forward propagation and backward propagation. In backward propagation, the idea of learning, when we say that idea of learning, we have to see that where is the gradient you can say are diminishing, where they are vanishing, what's the issue coming up, and is there some barren plateau or there or not. So how to handle that, we need to do that particular phase iteration by iteration, whether we are using gradient descent or stochastic gradient descent or batch gradient descent, any type of algorithm. So sorry, any type of optimization technique. So we need to do these we need to handle these fine phase controls, and this particular fine phase controlling will actually lead us to some better results. So yeah, little bit of what exactly needs to be done with respect to these gates, that is S and T gates. Now a quick summary of what we have discussed till this point. So the pattern that needs to be remembered is that X, Y, Z, they flip something, whether it is a bit or it is a phase. X is focused on bit, Y is focused on bit plus phase, and this phase is coming, and this phase is actually Z. I think it should have been on Z. Yeah, let me correct it right away. So uh, this is Z. So X, Y, Z. So phase flip is being done through this Z gate. Now, what exactly H does? H creates the superposition. That's the main idea, and whereas the S and T are like doing tune phasing, that we are tuning, we are tuning the phase, and just like the idea of hyperparameter tuning, as we see in a machine learning pipeline or a deep learning pipeline, we tune the hyperparameters step by step. This is how we are also seeing the SNT gates. So as we understand that all of them are reversible rotations, and X, Y, Z, and H are self-inverse, whereas S and T are not. They do not come back to the position that we started with. So if you apply uh, uh, Hadamard to zero state, as we saw, and again apply Hadamard, we will be getting back to zero state. And this is the same case with the other three gates, the X, Y, Z. So this whole summary is just one, is kind of a one genuinely one qubit vocabulary, and everything bigger than that, that is when we move towards some two or more qubit gates, we'll see that how that can be done. So this is the starting way to, or the best way to, kind of a way to connect qubits. The first idea we have, you can say, consumed in here. Now we are moving towards one very specific, very important idea. That's the backbone of everything that we see in with respect to multiple qubits, and that is tensor product. Now, what exactly is this idea? Hold on to your seats. It's this is the most, you can say, very profound idea of, and this is completely mathematical. Whatever we are doing in this particular tensor product and all, it is mathematical. It's coming from the idea of the vector spaces and the Hilbert space that we see. So to do anything interesting, we need multiple qubits. Till this point, before this slide, till this slide, we had seen everything in from a single qubit point of view. Whether it was yesterday's session or today's session, today's session till this point, everything we have discussed, it is about single qubit, how single qubit we do the superposition, how we do the interference, the measurement, entanglement, we saw briefly. But yeah, now we are moving towards the idea what interesting can be done with multiple qubits, and tensor product is the tool for combining them. So as we say that multiple qubits are combined with a tensor product, this is where the idea is. And the key consequence from the day one is that two qubits give four possibilities, as we saw. That is, n qubits is giving us 2 raised power n dimensional space. It means if we have 2 qubits, we have 4 different possibilities. 3 qubits will be giving us 8 different possibilities. So this space doubles with every qubit. So if we say that we have 100 qubits, we are saying that we can handle 2 raised to power 100 possibilities. That is, we have 2 raised to power 100 dimensional space. So this is the basic idea of a tensor product. Now, moving on to this symbol, it's a somewhat a new kind of a thing that we see. Earlier, when we see an addition and a circle around it, we say that okay, this is XOR and XOR operation, but this is a little bit different. We are seeing that it is a kind of a cross or a multiplication, and this is residing inside a circle. So the idea of adding a qubit doesn't add to the space, it multiplies it actually. When we say that we are adding a qubit, it is not just it is not an addition, it is actually the multiplication. So the exponential is the whole source that we are understanding from this idea. Okay, one example. Let's try it out, that how this 0 0 is coming out to be this 1 0 0 0, and that is the column vector. Let's see this quickly. So it's written like this. Okay, I can write it out. So like this. This is also another way to write it, and it's You understand this quite quickly. I'm not very good with trying to, so pardon me for that. I might be not writing it correctly. Why I have written like this, so that you understand what exactly is happening. Now, zero. I hope everyone understands this. Is like what? It is 1, 0, and this is 1, 0. Now, we are saying we have got this result. Let us see, let's put it as like this. We are saying we have got this result 1, 0, 0, 0. Now, okay, we know the result. We have reached this point. Now, how to get this? So what this is what the idea is all about. So we write it again, but let me write it more clearly. We write this both these things again, this, and write it like this. Now what is happening, that this one is getting multiplied just like matrix multiplication with this whole matrix, this column matrix, and this 0 is getting multiplied just like the matrix multiplication with this whole matrix again. And this is how we are putting this in this column matrix. Let us try to see. So with this, we get this 1 into 1, that is 1, that's the result. 1 into 0, this is 0. 0 into 1, this is 0, this is this result. And 0 into 0, this is this result. This is how we get you can say this particular result. If you see this 0, 0, we get 1, 0, 0, 0 transpose. And for this 1, 1, I hope everyone will be able to understand how we are getting this 0, 0, 1. So 0, 1 and 0, 1. So what we will be getting 0 into 0. So now you do not need to like write it like this. You can say verbally also do this. Uh, am I is my screen being shared? Is it okay? Ma'am, Shishmita ma'am, can you confirm please? I hope it is sharing because it's showing me your screen sharing is paused. Can anyone confirm? Maybe through chat only. Is my screen is sharing or not? Anyone? Okay. One second, one second. One second, I'll show you. Sorry for this. Yeah, I hope it is visible now. Sorry for this. I thought it was sharing. That is why I confirmed. Okay, so what I was saying that this 0, 0, as we see what it is like, we are writing this 0, 0 in this form, the 0th state and the 0th state, and we are writing this value like this. Where is the PPT? Yeah, this one. So when we say that 0, 0 is giving us this answer, what exactly we mean that this 0 state tensor product, 0 state, we can use, you can say apply it like this. Now this 0 state is actually this, as we saw it earlier also, and this again 0, this 0 state is this. So now what we happens when we multiply is we are getting this result. That is okay, we get this result, we understand this result, but this idea of how we get to this result is this one is written in here, and we multiply this matrix multiplication, we multiply this with this whole matrix, that is the second you can say matrix, this column vector, and this 0, that is the second element of this first matrix, we are multiplying it with this whole matrix, and like this we will be getting our results. That is 1 into 1 is giving us this particular you can say result. This 1 into 0 it is giving us 0. This 0 into 1 is giving us 0, and 0 into 0 is giving us this 0. So I hope this is now clear to everyone that what exactly is happening. Let me show you again so that you understand. Uh, Real sorry for not showing it earlier. Thought it was sharing. Now let us do this same activity for this 1 1. Okay, so you will understand very clearly. So 1 is the product. 1, what is this one? This is this matrix product. So what exactly are we doing? 0 into 0. So let me show this again with respect to that. 0, 1. So this way we get 0 into 0. This has 0. 0 into 1 as 0. 1 into 0. This is 0. And 1 into 1. This is 1. Now, take this as kind of exercise or anything like that. You can do after the session maybe. What exactly will be coming? This will be coming out to be, and what 1 0 will be coming out to be. This is a very simple, you can say, idea that you can use in here. So this is the basic understanding of what exactly goes on with respect to the idea of tensor products. Now, moving on, we have the idea around what happens when we use this tensor product, to actually model product states and entangled states. That is, when we multiply this A and B, that is, as we just saw, 0 and 0, 0 tensor product 0. The qubits are independent in terms of a product state factors. But in an entangled state, they cannot be written as any tensor product. This is very, very important distinction. So what we are trying to say is that in a product state, both the you can say states are independent of each other, whereas in the entangled state they are not separable, they are not independent, and a product state is separable state. You can also understand the idea of product state as a separable state and entangled state as non-separable state. So the idea of single qubits that we saw, single qubit gates can never create entanglement. So the for creating entanglement, we need a gate that acts on two qubits at once. This is what the idea of entanglement is all about. I hope this is okay. This is clear to everyone that what exactly is the difference between a product state and entangled state. If everyone is okay with this, then we can move ahead. Otherwise, I'll just wait for 30 seconds. If there are any questions with respect to a product state or entangled state, you can ask quickly. Any confusions with respect to product or entangled states? No? Okay. Let's move. So we have been discussing this entangled product state again and again. How actually we this happens, this is applied, is through this C not gate, that is the controlled not gate. Now, what is this controlled not gate? This is the workhorse of multi-qubit computing. The rule is very simple, that if the control qubit is 1, you have to flip the target. And if it is 0, we have to leave it alone. Now, what exactly is a control qubit and a target qubit? Maybe I can use thing, can use it here. So this is what we see in the terms of this is a control qubit and this is a target qubit. So what we are saying that if the control qubit, if the control qubit is 0, then the target qubit remains as it is. We do not change anything. But if the control qubit is 1, we change the target qubit. Let's say an example. This 0 is our control. This is our target. So there is no change in here. That is control is 0. Target is, it remains same. Control is 0. Target is 1. So you see there is no change. That is 0, 1 remains 0, 1 only. Now control is 1. So target currently it is 1. Sorry, 0. It will change into 1. So this is why there is a change. And control is 1 again and target is 1. So it will be changed to 1, 0. Now the matrix for this particular you can say idea is somewhat like this. Let me show in here only so that you can understand the matrix. So matrix is like this: 1 0 0 0. That is first row is same. So erase that. That's wrong. Then 0 1 0 0. Now in identity matrix, what exactly goes on? It is like this: 0 0 1 0. But this is not the case in C naught matrix. If you see this C naught, in C naught 1 0 is changed to 1 1, and lastly 0 0 1 0. So this is the C naught gate or the C naught matrix. 1 0 0 0, that is corresponding to the this first uh, pair. Then 0 1 0 0 corresponding to a second pair, 0 0 0 1 corresponding to the third pair that we have flipped. We have flipped these two and we have flipped these two. So this is the basic idea of a C naught matrix. And this is the whole point of this C naught idea, that we put the control in superposition and C naught links the two qubits into an entangled pair. So when we see the notation in, with respect to Qiskit, we have to keep in mind the idea of the how it uses Little Endian format. So the notation is that will be used is like control then target, but Qiskit actually prints qubit 0 on the right. So it will be a little bit different. That is flipping will be there, and we will come back to we'll go back to the how this actually happens. So this is the matrix with respect to the controlled NOT operation. Now another idea corresponding to the controlled operations, that how controlled operations are seen in general, is controlled U, another is controlled Z, or it is one another type of you can say matrix, or you can say gate is CCX. That is control not. We are saying control not. It is a 3-qubit gate where we have two control qubits and one one target qubit. So C naught is just the most you can say famous member of this particular family, that is the controlled operations. We can make any gate conditional, uh, and how this can be done. It is like do this, but only if the control is 1. So we can make in that particular sense. So control Z or control phase and anything like that we can make. And we can have this two controls like this Toffoli gate or the Fredkin gate. We can do that also. So the two controls give us the liberty of this gate flips. when both of the control qubits are one, and it flips the target based on that. So this can reproduce any classical logic, and that is why the control gates are how quantum circuits absorb everything the classical circuits can do, and then also go further. And last gate that we need to understand is the swap gate. So with this understanding of all the gates, we will be good to now do some uh, see some understanding of how this whole workflow, we can say, goes from from start to end, and what uh, how these particular gates can be applied in hands-on. So swap just exchanges two qubit states. It looks trivial, but it matters on real hardware where not every pair of qubits is physically connected. So sometimes we have to shuffle these states around to bring them together. So swap is like really three C naughts in disguise. It is like that, that when we apply three C naughts, you can say together, we get the swap gate. And this actually reinforces the idea that C naught is the truly fundamental two qubit operation. So this is the basic idea around swap gate. And a quick summary of what exactly is happening with respect to all these gates, that these multi-qubit gates. C naught, 2 qubit gate, controlled U or CZ is also 2 qubit gate, swap is also 2 qubit gate, whereas Toffoli is a 3 qubit gate. So in C naught, as we have seen, it is a conditional bit flip, and it is the primary entangler. That is, we do everything using this C naught gate only. And the controlled U is just applying the U or Z if the control is one. So it specifically comes from the point that if control is one, then we can apply U or Z, whatever gate we require. And swap is, as we discussed, it is just through three C naughts in disguise. And Toffoli is the idea that when we flip the target when both the controls are one. So you do not need to remember every gate in here. Only the C naught, the T gate, and the Hadamard is enough to build any quantum computation. And let us see that why is this such a, you can say, powerful idea. So the idea comes to understand that how a finite alphabet can be made using this standard example of H, T, and C naught. And this is like one of the most elegant facts in this field. So that you understand that you do not need infinitely many gates. Only a small fixed set can approximate any operation. And this can be done to any precision you like. So it's like the exact parallel to the classical computing, where the single NAND gate can build everything. So I hope everyone knows this, that we can build, can say, every classical circuit using a NAND gate, and a finite quantum circuit, can say, can build every quantum circuit that has H, T, and C naught in its, you can say, arsenal. So the idea of how this runs in real hardware, uh, we have just a few native gates in there, and Qiskit's compiler like quietly translates your circuit into them. So let's now take a little we can say pushback, and before going to the quantum circuit model and other ideas, that is the quantum circuit model and the workflow and how we actually build a build state, let us now move towards the hands-on idea, that what exactly is going on with respect to yeah, one second. Yeah, with respect to the idea of these how these circuits actually work. So starting with the first idea, uh, this is the setup that we need, and specifically this is the uh, is this okay? Should I this little? I hope it is visible now. Or should I maximize or it more? Bit more? Yeah, I hope now it is okay. So the first idea, a setup. What happens with this setup is we are importing some specific libraries, namely the NumPy, and they are importing the quantum circuit, transpiler, the state vectors, operators, air simulator. So what this will actually be help, it will be through these libraries only. We will be building up our circuits, and the idea of this shorts and all, that we use 1,000 shots, and we run our circuits accordingly. So and return the measurement counts, that how this particular measurement runs. So this is what the basic setup is like. Would everyone like to like do this side by side? Should I like share this code? If yes, I can share this code in the chat, and everyone can do like likewise. What do you guys say? Should we do it okay, side by side? Okay. So I hope everyone will be using this now. This chat. Yeah. So I'm sending it to everyone. First of all, this is the setup. So we are starting with the setup part. Then uh, first of all, you will have to do a specific thing in here. Let me go back in here. Yeah, you will have to do one specific thing. What is that? Uh, you will have to run the terminal and go to the new terminal in this VS Code. First of all, you will open a new file, and what this type of new file will be, it will be a Jupyter notebook. Let us do this. We'll do this one by one. Let us do this like this. We have a Jupyter notebook. We are starting with this right now. If you see, I am at base. I'll be going to activate my environment. That is this QCQ, a quantum computing workshop. It is like that. So I had built up this environment. I am activating this through this terminal, and as soon as I run it, I will be now in my QCQ environment. Now, let us do this one by one. Let us copy paste this and run this in this Jupyter notebook. Uh, so it asks for us for this that is terminal. It is now running clearly. Now done. Second part that we have, that is smaller, so it is accessible quietly. So this was the second part, that is the warm up. So let me generate some codes, snippets. So yeah. So this is the basic superposition task that we had seen. I'm also putting this simultaneously on chat, so everyone is seeing this on chat. Now, this is the first part, and let us close off this terminal. So through this header, what we are seeing, that we will be getting a superposition of a 500 kind of a you can say result. If we run it again and again, we can get different solutions. Now, moving towards the core understanding of what exactly is happening today. This was done earlier, so I'm not explaining that again. And now we'll go to this idea one by one. Now, first of all, let's put it in the chat. This is the idea around. Okay, let's put this in here. So what exactly is happening uh, in this understanding, in this idea, is if you see this, what exactly we are focusing on, the named states, that is the plus and minus. It means they will have same probability, but the phase will be different. And how we are seeing this? Plus state, as we see, it is like this at 1 1 and square root 2 that we are understanding. And the minus state, the changes in this minus the sign, that is this sign will be telling us that how the phase is actually changing. And we are just seeing the probabilities, that the probabilities will remain same, whether it is plus or minus. It doesn't matter, probabilities will be same, because when we see the amplitudes, that okay, these are the amplitudes of whether it is a plus state or a minus state, it will come out to be what, the square of whatever value we had. That is, 1 square is also 1 and minus 1 square is also 1, so there is no problem. But are they both same state? That is what we are trying to decipher in here. That is, whether the both these states are similar, the answer will be coming out to be as false. Why false? Because the idea is that phase differs. That is why I have written this uh, comments also, so that you can understand what exactly is happening with respect to this. So phase is differing, so we can't say that the phase, that is the state, are same. Let me just remove this and let us try to see that what exactly now we will be getting the answer as. Second, yeah, let's put this as plus, and this has also plus, and plus in here. Now, now let us try to see what exactly is happening. If you see the change, that is, it is now showing that the the states are same. Why? Because of the idea of having both the states as plus only. So this is the basic understanding of how plus and minus, or you can say the phase, actually differs. So this is the basic idea around it. Let me do it back so that you can understand the difference. Okay. Now, moving on to the next idea, that is relative phase, how we can see the relative phase, and how we can see the global phase likewise. So, sorry, it's global phase we won't be able to see specifically, because it is unobservable. So we can only see the relative phase only. So in the terms of relative phase, what is happening when we see this Bloch sphere, that is, we display the Bloch sphere with respect to the plus state, that is when we apply Hadamard to the uh, zeroth state, we will be getting this Bloch sphere. And when we apply Hadamard to the minus state, we will be getting the next Bloch sphere. Let us see this live also on the Bloch sphere. So we have quantum gates. Uh, when we apply Hadamard, it will be coming towards this. And when we apply, when we first change it to 1, and when we then we apply a Hadamard, it will be going towards the opposite side. So as we just apply Hadamard to it, if you see, it is making this 180-degree shift, and it is going towards this X state, or we can say the X direction, not a state, X axis. Okay, we undo this because we can't do this on the same idea. We apply first the X, that is, it is taking a 180-degree shift again, and uh, the state changes from 0 to 1. And then we apply Hadamard. That is, we are applying Hadamard to the state 1. So it will be giving us what? Negative, the minus state. And what this minus state is like, if you see, it is making a 180-degree shift. Now if I just change this, if you see this, it first went from 0 to 1 like this, and then it took a 180 shift. We show it like this, 180 shift from this to this. So it is just the opposite of x. I hope everyone is understanding what exactly is happening. It went from 180-degree shift in here and then 180-degree shift in here. That's the idea that's being used in this particular understanding. Okay, let us come back. Where is Visual Studio? Yeah. So this is the idea with respect to this relative phase. I'm not sending this. It is a very basic idea. Let's not send this, as I will be sending this whole you can say uh, file at the end of the session. Now moving towards the gates, we are now seeing the gates as matrices, and what these gates are: x gate, the y gate, the z gate, h gate, s gate, t gate. So what exactly we are saying, that for all the names in this is just a Python code, nothing else, very basic idea. For all the names in this, we want the round, you can say, the operators, how these operators data is going to come in here. So x gate, if you see, it the everything is written in the terms of the complex numbers. That is, if it is 0 only, that is it is written as 0 plus 0 j, and likewise it is written as 1 plus 0 j. So 0, 1, 1, 0, this is what the matrix is all about. Why 0 minus 1, sorry, minus I and 0. If you see this, this is j, so this is why it is important to write it like this. So this is 0 minus ij. For z, it will be 1, 0, 0 minus 1. For h, it will be 1 by root 2 at the outside, and you can write it as 1, 1, 1 and minus 1. Likewise, you can also do the uh, 1 by 0.707, that is 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. And for s and t, it is 1, 0, and 0 and 1. So like this, it is just it is just the square root of you can say z, and t is just the square root of s. So this is the basic idea around these single qubit gates. Now moving towards how the phase changes. If you see this, we apply the uh, Hadamard, and then we apply the S, it will be just adding a 90-degree phase to 1. Let us see this in Bloch-sphere. When we apply Hadamard, it is going to a superposition, and then we just apply S. If you see, it is just doing a phase change. It is doing nothing else. It is just changing the phase. How this is how we say that this is a phase change, because it is just adding a 90-degree phase in the terms of that particular state that we had. So the in the terms of state vector also see. Now this way you will understand more. If you are saying this, we have the state vector like this. When we apply head s to it, what exactly is being changed? This value is as it is, same, nothing else, but the phase, that is we are now getting it in the terms of a complex value. So there is a phase change in that particular one state. So this is what the idea is all about, and mathematically you can also see this, that when we apply Hadamard, in when we have a superposition and when we apply s onto it, what exactly, how it exactly changes. Come back to T also. It also see we also see it in that sense. For tensor products, we had already seen this idea, that how combining the tensor product will give us 2 raised power n space. That is, from 1 qubit we get 2 dimensions, from 2 qubits 4 dimensions, and likewise. So this is the idea of tensor product. We specifically saw this in here. This is tensor product of 0, 0, and this is tensor product of 1, 1. I have this provided you with this to do it and at your pace. What will be the tensor product of 0, 1, and what will be the tensor product of 1, 0. Very important idea, because the idea of product states and entangled states, it stems from the idea of tensor states, a tensor product only. Then the C naught gate. Now, okay, let us see C naught gate a little bit in action. For that, we will need to change it to 2. So we have 2 qubits. The resistance is also 2. Now, let's start this one by one. Oh, sorry. Yeah, I think it is not here. Should be there. Okay. So we are right now we are at state. We can say we are starting with 0 0. That is the state 0 0 is at 100% probability, and the state vector is also showing us that it is 1 0 0 0. So if you understand it, what it is currently, it is a tensor product that we just saw. Now I am applying Hadamard to this first qubit. Uh, it is actually different bit ordering, but let us for the sake of understanding, I'll put it as 0 in here only. Otherwise, if you put 0 Hadamard in here, if you see the state vector, it will change. The state vector has changed. Now state vector is showing that 0 0 and 1 0 are at 50% probability. So depending on what is the bit ordering, that's what the major idea is. But mathematically, if you do this, you will understand what exactly is happening mathematically when we apply Hadamard. Let me show you quickly. When we apply Hadamard onto 0 0, so 1 by root 2, 1 1 1 minus 1, and we have 1 0 0 0. So when we do this operation, that is when we apply this operation, we will be getting some specific, whether it is 1 0 1 0, something like this, or sorry, it should be 707 in this same state, or so you can understand this specifically, that it depends on the bit ordering, nothing else. Mathematically, how what exactly you will be getting, you have to just uh, like do this particular operation. Okay, and this is a 4 x 4 matrix. This is a 4 x 1 matrix. So whatever you will be getting, it will be a, it's a 4 x 1 matrix, just like this. Okay, so 1 by root 2, when we have, let us do this quickly. 1 into 1 plus 1 into 1 into 1 plus 1 into 0 plus 1 into this, 1 into this. So it will be 1. Then likewise, if you can get this particular ordering in that particular sense, that how these values are going to be there. So I'm let us leave it. We'll come back to it. Now, C naught. When you apply C naught onto this Hadamard, because what we were discussing, that superposition after superposition, you need a controlled NOT gate, and this controlled NOT gate is actually creating entanglement. So when we put this in here, see the change, how this basis state is changing. Now we are getting 0 0 and 1 1 with 50% probability. This is probability. This is not right now we haven't measured it. So it will be exact 50-50. So we have 50 in here, 50 in here. This is what we have got. And this is the computational basis state we are getting right now. As soon as we measure it, we will be getting our particular results. So when you double click on it, I am just double clicking on it. You can change the control. This is control bit, the control bit, and this is the target. So right now control is Q0 and the target is Q1. We can change it. We can just put it as Q1. Now, if you see this, your state vector has changed. Your state vector has changed. So this is the another you can say way you can get the superposition. Now put it back in here and let us measure this. And after measuring, what exact result are you getting? This is what we are trying to see in here. So as we measure this, the first, it will be giving us that, okay, you have measured the first qubit. So we are getting this 1000 as the idea around the Hadamard 00 tensor product. And again, when we measure this, now what exactly are you getting? This is the amplitude, that is 00. This is the amplitude 00, and the probabilities are now what? 00 and 11. This is what you get after the measurement of this state. That is, we started with Hadamard, we applied this C0 gate, we got superposition, we went into the idea of superposition, but uh, and the C naught gave us entanglement, but as soon as we measure it, we will be getting this particular result. That is 00 state is coming with full amplitude, that is 1, and other states are not present in here. And the state vector for this is like 1000. So seeing the same thing in here also, what exactly is happening? The C naught truth table that we had seen, it is very basic idea. Uh, we have seen already the product and the entangled state. This is also we saw for how independent qubits and entangled, you can say, Bell state, how this differs. I will come back to the swap in a little while. First of all, we'll try to see this first idea, the Bell state idea, what exactly is happening with respect to this Bell state, because this is much more important than the other ideas that we have before that. So just a quick note on what exactly is happening with this Bell state generator. We can use different combinations. One of the combination that we have just used is Hadamard plus the C naught. We can use some other combinations besides it that are there to show different, you can say, Bell states. There are 4 different Bell states that you can get. So what specifically are there? Let me show you. These are the 4 Bell states. That is phi plus, phi minus, psi plus, and psi minus. And every state is produced by the same H plus C naught circuit, but how this circuit is applied to different input, this is what the idea is. This is where the idea changes. So you can try this on your own. When we here it is, yeah, you can try this on your own once, that what exactly is happens when you apply Z on qubit 0 and after the H, how this gives us this state, that is the phi minus, one of the Bell states, or X on qubit 1 before the C naught, it will be giving us a phi state, whether it is 0 1 or 1 0, and any of that. So this is a kind of a practice exercise that you can try. We are seeing this here only also, that how this is actually done. Let us come back now. Let us now go step by step. So why the extended discussion about C naught? Because this is the basic idea behind everything we see in the terms of entanglement. So what exactly is being done in here? If you see this, that we are just applying uh, we are just seeing the C naught matrix that we that we have seen earlier, nothing else. So this is just a one way of showing it, that if we have the control 0 and the target 0, we are getting 0 0, and same for 0 1. We will be get for 0 1. How we will be getting this? It will be it is written as 1 0, but actually how it is being you can say read. It is being read as Q1 Q0. So one important thing, this 0 1 is what? It will remain 0 1 only, but it is being read as in this form, that is Q1 Q0. This is what the ordering is all about. That is what I have been reiterating again and again. The later Indian ordering, it becomes confusing. That is why it becomes confusing. So this 0 1 is actually 0 1 only, but the ordering is different. That is what the change in here. If the control is 1 and target is 0, what we will be getting, it will be 1 1. So again, in here it doesn't matter because both are 1, but the ordering is like this: q1 q0. And lastly, for 1 1 we have 0 1. It means q0 is 1 because control is 1, so target is changing, and q1 is actually 0. So please keep in mind this idea of ordering, because as soon as you uh, this is what we are presuming, that everything we are doing is with respect to this Qiskit IBM Qiskit platform. What about what if you use some IBM Penny Lane you can say platform, or Google's Circ platform? Then the whole idea changes. So this is where you need to understand that this ordering is actually very, very important. Sorry. So in the idea of product state and entangled state, we had discussed that in product state, the idea is that the qubits are independent. They will be they can be uh, uh, they will give produce result as in the terms of uh, independent states, and in the terms of entangled you can say cube state, we will be getting bell state, a kind of a bell state, and it will show us different 4 types of amplitudes that we have. So this is the idea with respect to that. This is one of the bell states. If you see this 0.707, this is 0, again 0, and this is last is for 0.707, and this is what we have been getting in this in here only. If you see this one, if we change this orientation, then we are getting actually this one, and this is what the ordering is all about. uh, if you see this, yeah, this is how the ordering changes. So I hope everyone is understanding this, what exactly is happening with this idea. Coming back, swap. Swap is exchanging just the 2 qubits, nothing else, no problem any soever. So whatever qubit we are currently in, it will be just swapping that. That is 0 1 becomes 1 0, and nothing else. So that's not much of a problem. Now, the idea of workflow, as we were yet to discuss the why this idea actually works. That is in the quantum circuit model. We have been seeing this ordering and all. That is perfectly okay. Now, the idea with respect to this workflow is that first of all, we need the problem identification, how we frame the task in the terms of a circuit, and the state preparation. This is the most important, most fundamental idea, and this is very expensive idea also. Or we can say expensive, not idea. It is an expensive operation. Uh, this idea, this particular idea, the state preparation or the encoding, quantum encoding, this will come in handy as soon as we start the first step in on day 4 about quantum machine learning pipeline. Because how classical data is changed, or you can say converted in the form of you can say to be used by quantum circuit, this is the first most idea. That is the state preparation, how we prepare the state. And this is also one of the bottlenecks that is known as data loading bottleneck, that actually tells us that uh, this idea can be as expensive as we can say use some classical methods. So we have to use this very, very judiciously. Then the circuit design, the execution, the measurement, and the result interpretation. Let us try to see this in this step. The same step, the step-by-step process that we were seeing, it is like that only. What we are saying that QC dot at 0, it means we are applying Hadamard onto this Q0. It is the idea with respect to the prepare. We are preparing the qubit for some operation, and right now we have just put it in the superposition. Then applying the this q naught, also it's the c naught, is like we are now operating it, and it is we are entangling, we are doing some entanglement. And the measurement, as soon as we measure this, that is with respect to the first and the second qubit, we are seeing the whole workflow in this one particular circuit. That is, we are preparing, then operating, and then measuring. This is the basic idea around this workflow. Then the idea of how Bloch spheres are used in, if you remember this, so we have seen this now again and again, that how this Bloch sphere is being used in being harnessed to show the state vectors, and how this multi-vector, you can say this state vector can be seen from various aspects, whether it is x state, y state, or you can say z axis. So different views have been seen. If you see, if you observe this, we first saw this pointing towards the North Pole, then in a superposition, that is the Hadamard applied to the plus to the zero, then Hadamard applied to the negative state. That is what we the Hadamard applied to, sorry, one, so that we get the negative state, and then this is the South Pole. So these are the four ways of seeing this particular gate and states. So we are exploring this. Second idea around is what exactly goes on with a quantum coin toss. So in a quantum coin toss, we see that when we toss a coin, classically, when we toss a coin, we need to do the random experiment, or that, as we say, that there is some random you can say variable, and this random variable will give us some expected value. That from expectations we get some specific value, how many times, how many times we coin toss the coin. So if we toss the coin 10 times, what exactly will be happening? If we toss the coin maybe more than that, then what exactly the change is happening with respect to the different results. But in the terms of this quantum coin toss, what is being done in here is that the fundamental randomness is coming up if we uh, uh, just do this again and again. The change that is being seen in here is, if you see this, we can see this many a times. What the change in here is that classical mechanics, that is a Newtonian mechanics, fails after a certain point, that it is not able to justify that what exactly is happening with respect to some experimental techniques that you can uh, visualize in here through this quantum game. And this is very interesting. You enter into play quantum game and use it as virtual box. So if I think setup is not there. So yeah, maybe I'll show this tomorrow in tomorrow's starting you can say session, that how the prediction of actually the uh, uh, the coin toss that we are seeing, it is somewhat, we will model this same in that particular sense, and how this is failing after a certain point, that is classical mechanics or the Newtonian mechanics is not able to answer that why this phenomena is actually occurring. So this is what this quantum coin toss is actually telling us. Then the generalization of this random number, that is n-bit random number, we just saw. This is quantum random number generator, and this idea of quantum random number generator is very pivotal for the cryptography, because through this we can generate this can generate different combinations, different random numbering, and this is the backbone of, you can say, the quantum cryptography and the post quantum cryptography. So what exactly is being happening in here, if you see this, that we are just building up a quantum circuit that is having n you can say qubits and n classical bits. This is nothing else, just we are generalizing this particular you can say circuit, that is 1 1. When we had 1 1, it was just a simple coin toss, but now when we have n comma n, that is we have n qubits and uh, uh, classical bits, then we are just seeing from that particular range that how in different shots in 2000, if we take 2000 shots, all the outcomes, all the 8 different outcomes that we have, specifically because n, what we have seen, what we have taken, n equals to 3. So all the 8 outcomes will be somewhat coming equal. So this actually stems, this actually inspires the idea of how it can be, you can say, used in the terms of quantum cryptography. Let me run it one more time, and you can see the variation of the results. If you see, you are getting different variation of results. And the last part, very important, uh, we will come back to this again and again in the next 3 days. And this is the Bell state generator. And this is the idea of 4 different states that we were discussing. And you have to identify that which one you have made. It is like just the uh, uh, idea that you can use again and again. And I'll be sharing one uh, resource, very useful resource. Maybe I can show you quickly. Yeah, this one is. This is very useful resource. You can understand from it that how exactly these Bell states are formed. So psi plus phi minus psi plus psi minus. These are the 4 different types of Bell states. And this is the first Bell state that we just implemented and the mathematics around it. If you see this, this is what it will be coming out to be. And we start with this, that is this tensor product, and we apply Hadamard to it. Sorry, this is Hadamard. We apply, we have the identity gate, and we just do the Kronecker product of this Hadamard and I, and we get this 4 cross 4 matrix. And this 4 cross 4 matrix is then multiplied by this we can say 4 cross 1 matrix. This is why I think when I was doing this, I think it was wrong in here. It was a 2 cross 2 matrix. That is why I was not getting the intended result. Yeah, sorry for that. So it should be just this Hadamard, and then we get this 4 cross 4 matrix. And then this can be multiplied by this 4 cross 1 matrix. So this will be giving us the result, intended result. So the Kronecker product of this Hadamard with the identity is giving us this 4 cross 4 matrix. And this is actually uh, uh, multiplied with the 4 cross 1 matrix of the tensor product of 0 0, and this gives us this particular state, that is 1 by root 2 1 0 1 0. But this is, it's still not done, because we need to apply the C naught gate to this circuit. And when we apply the C naught gate, we get this I can say result, that is 1001, which gives us finally this state, that is 0011. And this is what we were getting in here. Oh, you see this, we were getting this, that is 0011. 0 0 and 1 1. This is the exact result. And you can reproduce the 3 other results. That is when we apply the X gate, and that is the it becomes minus state. And then when we apply the C naught gate, the other idea is like to apply do it negation of this, and then apply the C naught, and lastly this again. So this is the 4 different, these are the 4 different Bell states that can be generated around this operation. And this is what you are seeing in here, that is phi plus phi minus psi plus and psi minus. And the idea of no cloning theorem, will discuss this tomorrow itself, because it's very simple, not nothing more. It's not a problem, but how we can use an entangled pair and not 2 different copies. This is what needs to be discussed. So we'll first start with this idea, that is the no cloning theorem, and then we'll move on to the idea of different quantum algorithms. So if there are any questions, do let me know quickly. Otherwise, we can close out the session. Are there any questions? everyone, I hope everyone has understood the concept around quantum states, quantum operations, quantum gates, how to build up different the four different build states, and the idea of uh, using single qubit gates and multiple qubit gates. Okay, so if there are no questions, then we can like close our session. Shishmita ma'am, you can like take forward.
Yeah, sure, sir. Thank you. We can wind up. We'll meet again by tomorrow.
Okay,
Thank you all.
thank you everyone for connecting.